So let's get started today. So Isaac, we're gonna come in to do a worksheet tomorrow instead of Thursday. That's the difference. Okay. And then also. Okay, so today I'm gonna try to get through as much material as possible in chapter 30 and still have it somewhat make sense. I'm not sure if it works out that way. So I'm not going to be doing a lot of examples, but I will kind of, talk about each of the example and what each of the example will show you if you do just kind of go through it in the book. And also the video lecture I'm posting is from last year, so I did those examples in the video also, so you can actually watch it, and then figure out what I did wrong and stuff like that, right? So mostly today is going to be kind of concept, and then tomorrow you guys are going to come in and do the worksheet. Actually, on this thing, remember this thing? This is called a slide bar, where you have a piece of metal, right? And then it's on a rail, and then the way we're modeling this is that this little bar has some resistance to it, and then it says you move it to the right, it develops a potential difference between the two due to the fact that, well, let's just go down here. Let's just go back up here. Due to the fact that, as you move this little bar to the right, and it's in the magnetic field, so V cross B will cause positive charges to move upward and therefore negative charges to go downward. It actually basically emulates a battery, right? Because you have some more positive charge here, some more negative charge here, right? It basically creates a battery, and this battery is called a motional EMF, right, as opposed to just a regular EMF, right? So it's only creates the voltage source for you only if you are moving, right? And we're going to slide down here, and using that concept we talked about yesterday, we're actually able to calculate the current that's going through this little loop here as you're sliding it over to the right with some velocity v. This is a lowercase v, right? Remember, capital V, lowercase v. It's very different. Times the magnetic field times how long this little bar is, divided by the resistance in that bar. So modeling the bar with resistance, but then this rail, we don't model it with the resistance. We just assume the resistance there is 0. Okay. So now something interesting happened, right? The magnetic field with a moving bar created a current, but now you have a current in a magnetic field, right? So what's going to happen if you have a current in a magnetic field? Anyone wants to venture a guess? When you put moving charges in a magnetic field, what type of action or what type of thing will happen? I don't want to say the word. I'm sorry? Centripetal motion. If this charge is moving in a circle, yeah. But what would that motion came from? So in order for things to go around in a circle, what would you have to apply to it? I'm sorry? Torque or force, a centripetal force, right? So what happened is that if you have a current in a magnetic field, remember this from last chapter? If you have some current in some magnetic field, right, you can actually calculate how much force will be applied to that wire, right? Remember when you have, I don't want to drop this, right? When you have two current that are parallel to each other, one is creating a magnetic field, the other one is feeling the force of the magnetic field, so they will actually be attracted to each other, right? When the currents are going in the opposite direction, they actually repel each other, right? When you have current in a magnetic field, it's going to have a force on it, just as if you have a single charge in a magnetic field, it's going to feel force, right? And this force we actually calculated last chapter, right, is the current that's going through the wire, multiplied by this weird cross product, right, which is L. L is actually the vector of the wire, right, with the direction and the magnitude of L, okay, cross producted with the magnetic field, right? In this case, if you just want to find the magnitude, is just, magnitude size, all of this, times the sine of the angle between them, okay? So the neat thing about this situation, the one we're in, right, the current, right, is going upward, right? The magnetic field is going into the board, right? And then so therefore your middle finger points in the direction of the force, so it's going to actually have a force to the left, right? So that's why I think last time I said, oh, if I flick this and then just have it go, right, there's actually going to be a force that's going to be slowing it down, okay? So actually what you need to do in order to keep generating this voltage and current on this little loop, you have to keep pulling on it with a constant force, okay? And the balance of these two forces will allow you to determine how much current or voltage you're going to get out of this system, okay? So for what we want to plug in this little calculation, remember the current that we calculated from above, up here, right? VBLR, so remember that. If I plug that current into here, right? VBLR, right? That's what this piece is, right? And multiply all this stuff together, right? The force that's going to be on the wire that's trying to slow you down is going to be how fast is moving. Like, it makes sense. The faster you're moving it, the more the bigger the magnetic force is going to try to slow you down. Okay, L squared, so it's actually proportional to the square of this length. So if this was twice as long, it'll be 4 times the force, right? If it's 3 times as long, it'll be 9 times. And also B squared, right? It'll actually square as the magnetic field square, divided by the resistance, because that's where this R came from, right? Okay. So whenever this happens, you actually have to pull it, right, with a force in order to offset the magnetic force so it doesn't slow you down. Okay. So once you have a force, may not be as obvious, right? You can actually calculate power out of it. So we're going to do a little calculation so we can actually calculate the power that is generated by this little power generator we made, just by sliding things on in a magnetic field. Okay. So remember power. Okay, just a reminder, right? Power is how much work something can do over some amount of time, right? So if I go play tennis, right, and I burn 10,000 joules of energy per hour. Let's not use hour. That's a hard unit to deal with. 10,000 joules of energy per 100 seconds, right? I am spending. So if I'm doing 10,000 joules of energy in 100 seconds, that means I am using 100 watts of power, right? A joule per second is a watt, right? Okay. So there's another way to calculate power, and I'm not going to go through the derivation, but it's just a couple of steps where you can actually find that, well, if you take the force and you multiply by how fast that object is moving, that also allows you to calculate power. Okay? Okay. So in our case, it's kind of nice because we can calculate the force, right? We already have the equation for the force that's going to be required by you to pull on this. If you're pulling force and the magnetic force that's trying to slow you down is equal and opposite to each other, then you would go at what velocity? It's not constant velocity, right? Exactly. And that's what we want. Okay. So therefore, right, this force has to be basically whatever the magnetic force we got, and then multiply the velocity once again. So basically it's just adding another factor of v, right? So not adding, multiplying by another factor of v. So therefore, the amount of power that comes out of these little, slide bar generator is just v squared, L squared, B squared over R squared. So a bunch of squares, okay? Okay. So you can actually generate power out of this, okay? The example down here, which I'm just going to go through it. It's pretty quick, okay? Let's do this example real quick, where we have a little slide bar power generator, right? And we're trying to light up a 1.5 watt light bulb, okay? So how can we do that, okay? So what is the speed that the wire, the slide wire have to be traveling in order to light up this light bulb to full brightness, meaning maximum power is 1.5 watts, okay? So the amount of power we want out of this is 1.5 watts, okay? And we actually have an equation for this, right, up here, right, v squared, L squared, B squared over R. So that's going to be equal to v squared, L squared, B squared over R, right? Let's just double check we have everything, right? So we have, well, V is what we're trying to solve, that's fine. We have L. L is actually 0.1 meter. The magnetic field, right, is also 0.1 Tesla. But R is missing. So how can we figure out what R is, right? So now this goes back to our resistor circuit stuff that we talked about in chapter 27, right? So for a light bulb, you can model it as a resistor. Remember that? Okay. Okay. A light bulb can be modeled as a resistor. Okay. So basically, if you have a little light bulb like this, I'm trying to draw it. How does the book draw it? So, okay, whatever this is, okay? This is supposed to be a light bulb. You can model it as a resistor, okay, with some resistance R, okay? So if it's a resistor, then it obeys Ohm's law, right? So change in voltage across a resistor is the current times the resistance of that resistor, okay? How does that help us get to R, right? So we still don't know what R is. But we can change this little equation here so that instead of putting in power, right? Power on the resistor is also the current times the voltage across that resistor from last couple of chapters ago. What we can do is basically substitute this in so we can get rid of the R. So let's see. So power. How do I calculate the R from this? Because we know the power is 1.5 watts, right? We know this side. We know this, but we don't know the current. So we want to calculate the resistance here. Okay, so the resistance, if you solve this for I, right, that's going to be, I can't do algebra at all this morning, I'm sorry. Right, that's what I is, and we plug it in here. The power out of here is delta VR squared over R. If you solve this for R, then you would get delta VR squared over the power, right? And these are the things that are given to us on the diagram. If we go up here, right? The voltage across that resistor, that's actually a light bulb, is 3 volts. The power is 1.5 watts, okay? So this is actually 3.0 volts square divided by 1.5 watts. And all of this is in SI units, so all the units should come out correctly so that we actually get ohms as the resistance. So that's 9 divided by 1.5. It's actually 6. This is going to be equal to 6.0 ohm. Okay, so we actually was able to find what R is by going back to chapter 27 and doing some V equals IR stuff, right? Okay, so we got that R is actually 6.0 ohms. Okay, so now I can solve this equation for V, right, and just calculate what that has to be. So let's go back to red. So V is actually wherever the power is times R divided by L squared B squared, right, all square rooted. Okay, okay. If you distribute these square roots, there's going to be P times R divided by LB. Okay, if I plug in these numbers, should be pretty fast. We have to move it. So 1.5 watts, that's the light bulb. The resistance is 6 ohms, right? 1.5 watt. Resistance is 6 ohms. And L is 0.1 and B is 0.1. Divided by 0.1, divided by 0.1. Okay, so I actually have to square root this thing on top. Let me know if I screwed up somewhere. Okay. For the magnetic field, put L instead? Yeah, the green. Oh, thanks. Yeah, that makes more sense. Okay. Well, both the numbers are the same. That's why it's okay to make that. No, it's not okay to make that mistake. So don't do that. Yeah. Okay. Okay, so if you punch this in your calculator, you get 300 as the answer. And since this is going to be a velocity and everything we plugged in was in SI units, this will come out in meters per second. So you actually have to drag this thing pretty fast in order for you to light a tiny light bulb, okay? So this is not a very practical way to light a light bulb, right? In the second worksheet that you guys are going to do on Monday, you actually have a little, they actually have a little device where you can do a little crank in order to light up light bulbs like that, okay? All right, so that's how you deal with this type of problem where, you know either the force or the power that you need to generate, right? And you balance the forces and the power in order to figure out how fast the little slide thing has to go, okay? And that's a very typical problem, okay? Okay, to balance those forces. So there's part B to this. So it's just basically if you want to calculate the force on it, you have to you can actually calculate what the force is by just plugging in V, L, B, and R. What I'm going to do next is actually cover this idea of eddy currents. So eddy current is created when you put a conductor in a magnetic field and you actually start moving that conductor, okay? It's very similar to what we were just talking about with the little slide rule thing, but it's slightly more complicated in this situation, okay? Because right up here you have a magnet, two permanent magnets, so the magnetic field coming out of these magnets are actually going straight down between the two sides, right? And out here there's going to be a little bit of magnetic field that comes out here, but as you go out here, you basically can assume that there's no magnetic field on the side, okay? So we're going to idealize it where we're just, kind of ignoring the part that's outside this magnetic field, okay? What's going to happen is that if you start to pull this little piece of metal out of here, okay, it's going to induce a current that goes around a circle like this. Let me erase some of the arrows because the book has plenty of arrows there already. Right, it's going to induce current that's going to be going in this direction on this side and going in this direction on the other side, okay? And this is the reason why they're called eddy currents. So if you imagine, if you take like a stick, right, go to the one of the ponds here and just drag it across the lake on the surface of the water, you're going to create these eddies like this, the same way, okay? And that's why these things are called eddy currents, because they look like eddies in water. But what's interesting is that this part of the current is inside the magnetic field. This part of the current is outside the magnetic field, right? So what's going to happen is that if I do my right-hand rule once again, right? If I have a current that's going into the board here, right? And I'm going to have a magnetic field that's going down, right? I'm going to have a force that's going to be pulling to the left, okay? Similarly, if you have a current, right, the current is also going upward in this little eddy, so it's going to have a force. All the force is going to try to pull it to the left, right? If I'm trying to pull this board out of the magnetic field, right, it's going to resist pulling it, okay? And that's the neat thing where I think one of you guys asked me about how does this superconductive train stop? This is how it stops. It's by putting a piece of metal between two magnets. So as the train is moving along this direction, this magnetic field is actually going to slow it down without actually even touching the train, okay? And we actually have a little demo for this, okay? So these are known as magnetic braking system, and this is typical on train because neat thing about train is there's already a piece of metal, right, on on there, okay? So what they do, these are the magnets, right? And normally it's lifted out, so it's not the train track is not between them. But as soon as these things gets lower, the magnetic braking engages, and you actually will start slowing down the train without actually touching the track itself. I mean, there are emergency brakes where it's like a physical brakes where you just clamp onto the track and that's where you hear the squeak, right, when the train tries to stop. But these magnetic braking is actually much nicer because you can actually recover the energy out of the train, right? Because what happened is that when you have a rail, right, and you put these magnets, right, next to the next to the tracks, right? This will induce current in the train tracks, and you can actually collect this current as electricity in the in a superconducting maglev track. You can actually get that power back as opposed to just losing it to metal grinding against each other, which is basically heat, which we don't get to talk about in this class. Okay, and so that's the idea of magnetic braking. Before we do the stuff to think, so I'm just going to show you a little demo. It's very similar. Okay. So this is a demonstration of the eddy current effect. I wish I was taller so I can actually hold this up. Right. So here I have two pieces of thing. One of them is magnetic. I'm not sure which one. Okay. So you would think that, well, if I put this down here, right, it falls. So it took maybe like a second for it to fall, right? Just as if I just dropped it, right? Same thing with this guy, right? If I just dropped it, it takes about a second for it to fall. Okay? So guess which one is the one that is actually magnetic? Okay? But the metal itself is not magnetic, right? It doesn't stick to it. Neither one sticks to it, right? Okay? So this is aluminum, which is a non-magnetic material. So that's fall regularly. So time how long that took, right? So let's see how long this one takes. Which one took longer? The second one, right? So this is actually a similar effect that we just talked about, where in the train magnetic braking situation, you have a train, right? And this is where the train is holding the magnet, and you're moving relative to the tracks. But this is the same idea where you have the magnet moving relative to the track, right? And it's actually braking, and the way it's braking is by offsetting some of the forces from gravity. Okay? And you can actually calculate this if you take the more complicated upper division physics class where you have to do three-dimensional calculus to do this, because what happened is that the forces you actually have are due to these fringe forces that's actually coming out. Okay? But that's the idea. It's the same idea, but just more complicated calculation than a railroad braking system. Okay? So let's do this stop to think, since we have a little break here. Okay? So let's say I have a square conductor, right? And I have this conductor moving upward in a magnetic field that's coming out of the board. Okay? How will the charges arrange themselves in this conductor if it was moving? Can we figure that out? Okay. I'll give you the little equation to figure out magnetic fields, right? QV cross B. Okay. So which of these configurations is correct? You guys figured it out, right? I don't see a lot of hands moving, right? Because usually that's required. Okay, yeah, the magnetic field is coming out of the board. Okay, so V is up. Okay, so let's do it together. So V is up, magnetic field is coming out of the board. So we're expecting what type of charge to move to the left? Positive or negative charges? Positive charge, right? But then we expect negative charge to move in the opposite direction. So which one of these diagram has that? Right, it's actually D, right? So that's how you figure out how the charges will arrange themselves. So this essentially, right, basically makes a battery, right, oriented in this direction, right, with some delta V of the motional EMF. Let's call it the motion, right? Right, and you can calculate this, right, using the equation we just derived. All right, so that's the idea of motional EMF. Let's move on to the next section because we're kind of breezing through this pretty quickly. The next idea we have to bring up is this thing called magnetic flux, okay? Just like electric flux, magnetic flux will also tell us something about the current that is actually producing that magnetic field, or actually the magnetic field is inducing some sort of current, okay? And we're going to see this thing called Faraday's law in a second, okay? So magnetic flux is a very similar concept as electric flux, where instead of, so you have some sort of loop, let's say, this loop, right? So this loop has some surface area, right? Right, this area vector, let me draw that in red actually, right? Right, remember these area vectors is perpendicular to the surface, right? So if I have a book like this, right, the area vector is actually pointing straight out of the book, right? And it points in whichever direction the book is pointing, right? So with that, right, just as the way we calculate electric flux, let me just write the electric flux formula. You're going to see that it's actually the same thing, right? E dot dA. Okay. So these are the same formula, but as opposed to having electric field going through this surface, now we're concerned with magnetic fields, right? So everything is the same except you're calculating it with respect to the magnetic field, okay? And the same tricks work, right? So if you have a surface like this, let's say your surface is flat like this, and your magnetic field is, oops, I'm trying to draw that in green. Your magnetic field is going in this direction. What will be the magnetic flux without doing any calculation? Zero, right? Because you're not impinging through it. But if your magnetic field is going straight up and down like this, right, and if it's constant, right, then the magnetic flux will just be, do they use B or M? Yeah, magnetic flux will just be the magnetic field times the area of that surface, right? So we're going to stick with these simple cases, okay? In this case, the example in the textbook that I actually went through in the lecture video that I'll upload is the less obvious one, where you actually have a changing magnetic field as you go further and further away from it. In that case, you actually have to do some calculus in order to do that calculation. And I show you that in the video lecture, okay? So we won't have to go through that in class. It turns into some weird natural log function, right? Because you're going to be integrating 1 over x, okay? So I'll leave that to the video lecture, and that way we can actually get through what we need to talk about for the worksheets that you guys have to do this week, okay? So the interesting thing about what we just talked about is that, right, there seems to be a way for us to calculate how much magnetic field is going through the surface, just the same way that we are able to calculate how much electric field is going through a surface if we have an electric field, right? Right? And remember how useful this was? This was a way for us to figure out how much charge is inside something, right? And we're going to use this, but in a slightly different way, right? Because only moving charges interact with magnetic field, right? Not still charges, okay? So what we need to do is actually have a changing situation. Okay, this is Lenz's law, okay? Okay. Where, going back to this little simulation I showed, oops, I typed L for some reason. Yesterday, unfortunately I didn't load the simulation, right? Remember when I take this magnet, right? If I have it sitting still, right? If I just place it and not move it, right? The light bulb does not light up, right? Only when I'm moving it around, that's when the light bulb lights up, right? So it's as if magnets, either magnetic fields moving or charges moving. One or the other has to happen for this to get in what's known as the induction of electricity, right? So this goes to a very useful law called Lenz's law, okay? Where if you have a, let's say a simple, very simple situation where you have a little loop, right? Don't even worry about how this little wire loop gets hanging in the air without touching it, right? It's just hanging up there in space, okay? If you have a magnetic field that is constant, meaning no change in magnetic field and no change in the size of the loop, okay? In this case, right, there is no change, well, so flux is B dot dA, right? But think about it as just kind of like, proportional to the magnetic fields times the area of the loop, right? Okay. In this case, if the magnetic field is not changing, the size of the loop is not changing, right? If you multiply these two numbers together, your magnetic flux is going to be the same, okay? Sorry. Okay, I know that the book does M instead of B, but I'm used to B. Okay, right. In this case, what happened is that no current actually gets induced. Remember, if I just hold the magnet next to the little coil I have from up here, right? If I just hold it still, I'm not changing the magnetic field at all, right? Nothing's happening. The light bulb doesn't light up at all, right? So nothing happens. Something has to be changing, okay? All right, so there's two different ways to do this, okay? What you can do is that, well, let's say, right, I have a magnetic field, but I'm increasing it over time, right? So once again, I'm going to write magnetic flux, right, as approximately, if you have a constant magnetic field, right, is the magnetic field times the area of the loop. If this is increasing with time, right, now we have an increasing flux, right? If we have an increasing flux, that means we're going to have an induced current, okay? But how do I figure out what direction that current is going to occur in, okay? And this is what Lenz's law is going to tell us, where, so since the magnetic field is increasing, right, so the flux is increasing in this direction, what's going to happen is that whatever the current loop is going to do, it's going to try to offset that change. It's going to try to undo that change. It doesn't like change at all, right? So what's going to happen is that, so if you're increasing the magnetic field this way, it's going to create a induced magnetic field going downward, okay? So if you know that the induced magnetic field is going downward in the loop, you can use your right-hand curl rule to figure out which direction the current is actually floating in, okay? Because remember, when you want to figure out the direction of, let's say I have some current going this way, to figure out what the direction of the magnetic field is, right, I point my right thumb in the direction of the current, and the magnetic field curves around my hand, right? Same thing here, right? If I know the induced magnetic field is curving this way, right, so it's kind of solving the problem backward, right, I know that then the current has to be going around this direction, okay? That's the direction of the induced current, okay? Okay. Similarly, okay, the magnetic field is upward, but it's decreasing over time, okay? If it's decreasing over time, the current loop is going to induce a magnetic field to keep that net flux constant. Therefore, it's going to actually create a magnetic field that's pointing upward to say, oh, I don't want to lose this magnetic field. I want to keep it the same, okay? It's not going to be able to keep it forever, but it's going to try to, okay? And that's the idea of Lenz's law, where it's going to try to keep the magnetic flux the same in a steady state, okay? Whatever the current loop is doing, whichever direction the current is going, it's going to try to offset that change. It's going to be trying to slow down the change, okay? It's kind of like a drag, okay? All right, let's not go through the downward ones because it's very similar except just opposite directions, okay? So let's do a quick example of Lenz's law, okay? So let's do this one real quick, just kind of, it's a pretty good concept problem, okay? So down here we have two loops next to each other where one is powered by a battery, okay? Down on the lower loop, we're going to measure whether or not we're going to get a positive current, meaning if current flows in this direction, right, it's going to swing positive. If the current is flowing the other direction, it's going to swing negative, okay? Okay. So let's figure out if I have a battery source here, right, since this is the positive side of the battery, right, I know that the current on this loop is going to be flowing to the right, and then up here, once we close this switch, right, it's going to create a current going this way, right? Okay. So if you have a current in this loop going this way, it's going to create a magnetic field inside the loop that's going upward, right? So you are increasing the magnetic field inside that loop, okay? Right? If the magnetic field is trying to be increasing here, right, whatever current gets induced here is going to try to decrease it. So it's going to try to make a magnetic field that's going downward, right? So if a magnetic field is going downward in here, it's going to have have to have a current that goes in this direction, right? Which makes actually the meter to swing positive. Does that make sense? Okay. So therefore, the red is actually what's happening. Okay. Because you're going to have I think the book draws it like a dot, dot, dot. So B induce, right, going downward, okay? Because this battery is trying to increase the magnetic field upward, right? The second loop is going to try to decrease it, okay? Okay. All right, it's got 10 more minutes. Yeah, I think that's, okay. So let's skip the stop to think. Sorry about that. It's in the textbook, so you can actually, should I just tell you the answer or no? Let's not tell you the answer, so that way you can think about it. Sorry. And you can just email me and ask me, okay? If you want to check the answer. So with Lenz's law, it creates this induced current, right? And what we're going to try to do is we're going to try to bring it back to voltages, right? Remember, voltages are easy to work with, right? So it's because there's just numbers. It's positive, then you're going to drive current to one direction. If it's negative, it drives current the other direction. And this is where Faraday's law comes up, and this is the part where we need to get to for you to get through the worksheet for this week. Okay, I'm just going to state Faraday's law as opposed to trying to justify it. We kind of already kind of see it because of this motional EMF stuff we've been studying, right? Faraday's law states that, well, if you have a changing magnetic flux, the magnitude of that change over time tells you exactly what the induced EMF is, okay? How big of a battery can you make, okay, by just changing magnetic flux, okay? Okay, and of course magnetic flux is more complicated, right? It has this, integral of B dot dA thing in there. So let's do an example with our, old trusty wire loop, right? Where we can actually do, visually see how this current gets created, okay? How this EMF gets created, okay? So in this little current loop, we're going to have the same setup where we have some rail that has no resistance, okay? And we're sliding something with the velocity v to the right, okay? So therefore, right, we already know that the current's going to flow this way, okay? We can prove this also with Lenz's law, right? How do we prove this with Lenz's law? So if we're sliding this to the right, we're increasing the magnetic flux, right? Right, into the board, right? So the magnetic field is going into the board, right? So whatever the current is getting created is going to be coming out of the board, right? To offset that change, okay? So therefore, right, if I point my thumb in the direction of the current, right, inside the loop is always coming out of the board. So right away, we know the direction of the current, or you can verify the direction of the induced magnetic field, whichever one you're trying to calculate, okay? So this magnetic flux, right, can be calculated by just multiplying, it looks like A times B, but it's the area of this loop times the magnetic field, right? The area of this loop, right, depends, right? This is just a rectangle, so this has some length L, right? And the position of the bar is at some position X, which depends on time, because we're moving it to the right, so it's increasing with time, okay? So therefore, right, the flux can be calculated by just multiplying X times L times B, right? This is a time-dependent variable, right? So just be a little careful, okay? So since we have that equation, right, therefore, right, we can plug it into our, into Faraday's law, where this is the magnetic flux, right? So we're just taking a time derivative of it. The time derivative of X times L times B, since L is a constant, right? B is a constant, right? Therefore, right, they don't get, they just pull out in front of the derivative. And if you take dx by dt, right, that's exactly what velocity is, right? So therefore, the EMF induced by this is just VLB, right? Which is exactly the same from section 30.2. It was the same result exactly, okay? So Faraday's law is just a way to generalize an analysis of this type of induced current when you're increasing the magnetic flux of something or decreasing it, that will do the same thing. Okay. If we put a little resistor in the loop, okay, we can also calculate the current just as we did before. So the idea of solving these type of problem is that you want to figure out what the function of magnetic flux is, okay, right? So in our case, right, it has an x times L times B, right? So that's the magnetic flux, right? You want to take a time derivative of it, okay? And be careful which thing depends on time. So in our previous case, the x is the only thing that depends on time, right? In the future, it could be y, it could be some, it could be the velocity that depends on time also, right? Okay, and that will allow you to calculate what the voltage, the induced voltage is on that loop. Okay, right. So from there, right, you can calculate exactly what the current is by just dividing by the resistors of that circuit, or anything else. And because after that point, it's just a circuit that we have dealt with before from chapter 27 and 28. Okay, because this basically just this is a think of it as kind of like a magnetic battery, right? It's just a battery that's created when you have a changing magnetic field or changing the size of the loop. Okay. All right. So there's more examples in the textbook that unfortunately we don't have time to go through, but I would wrap up with one last thing. It's this idea of induced field. Yeah, let me just get through this application real quick, because this is going to be related to what you guys are going to do on Monday on your worksheet. Okay, and this is with power generators. Okay, so I think I probably talked about this little sketch before already. So the way most of our power generation works in the world, actually not just in the U.S., is that we tend to burn something, make it hot, right? And what happens is that when you make something hot, the water will evaporate, right? And then the steam will rise up. Okay. Okay. As steam rises up, it drives a turbine. So there's a little turbine in here. Just imagine it as like a big fan, right? Just like a big ceiling fan, right? As the steam rises up, it'll turn the fan, right? Just as like a windmill does. Okay. That will turn a generator, okay? And turning this generator is actually what's converting the heat energy from these from burning coal or having a a nuclear fission reactor into electricity somehow. So how does it do that? Okay, and this was with the same idea as what we did with the electric motor before, but doing it in reverse. Okay, so inside the generator, you have a permanent magnet, and you have some wire loop. Okay, this wire loop has some area A that points in this direction. Hopefully now things are looking familiar. Okay, as this wire loops, get mechanically turned by the turbine, right? This is the fan. This side will be connected to that big fan that's the steam is pushing around, or you can just crank it yourself if you want, right? What will happen is that the magnetic flux, don't do that. The magnetic flux through this loop is going to follow some cosine function, okay? Okay, this cosine function, right, is going to be what we had in the first semester called a harmonic oscillator, right? Things going around a circle behaves as if it's a cosine function, okay? And then so instead of theta, where theta is this angle here, right? This theta depends on time, okay? What you can do is that, well, if you have an angle that depends on time, it's the same thing as, right? Depends on time. It's the angular velocity times the time, right? This is basically the same thing as distance equals rate times time, right? The same formula, right? Except in angular form. Okay. So once we have this equation for finding out what the magnetic flux is, okay? Remember, in order to get voltage, right, we need to take a time derivative, right? So if we take a time derivative of our magnetic flux down here, right? The EMF that gets created from this little generator, right? It's going to follow, okay, whatever the area of that loop is times the magnetic field between the two magnets. Omega, which is how fast it's spinning. So the faster you spin it, the bigger the voltage you get, okay? The more power you get out of it, okay? Times its sine function, which is going to be oscillating up and down, okay? And that's what this green function is supposed to be showing you right here, okay? Okay. So in a power generator, right, the voltage actually goes up and down, up and down, up and down, up and down, okay? Does that remind you of anything that we have in this room or what you're plugging into? Is alternating. So I don't like that name, alternating current. It's actually alternating voltage, right? The control is actually, we're actually alternating the voltage. And this is the reason why, you know, basically in all of society, we have alternating voltages in our socket as opposed to, you know, a constant voltage where, you know, will be more for batteries, okay? So, so that's what we need to cover. And I think that's what we need to cover for you guys to work on the worksheet on Monday also. Okay, any questions before we wrap up today? Okay. All right. So remember that Dr. Maktar is going to be in here working with you on the worksheet tomorrow. If you cannot come, you actually have you need a real excuse with like documents. Okay, I don't want to make it so that, you know, people just don't show up and it's just Anthony by himself, right? But you don't have to come to class on Thursday or Tuesday, okay? So you get 2 days off and you can do those lecture videos whenever you want.